next speaker, we'll have Hossein Haeri, who's speaking about using functional languages to facilitate C++ metaprogramming. So this really brings kind of the two coordinated wings together.
Yep. The name of God is Passion of the Merciful. This is Hossein, as I was saying. I work in SDS in Hamburg University of Technology. Today we're going to speak about the ways that you would perhaps use functional programming languages to facilitate the practice of C++ metaprogramming. So this talk will generally be a walkthrough the commonalities and differences across these two beasts. It will explore the possibilities for any semiotic translation across these two. It will, in particular, try to understand what are the commonalities and whether we can use that to facilitate any translation, what are the impediments, and whether that is really stopping us from any sort of thing. And we'll also explore a bit of whether there is any good idea behind an alternative solution. So, generic programming, this is the landed, I suppose. Some people say that it just doesn't feel that natural as OOP, especially when it slides into generative programming. And well, whether or not that's correct, what is certainly agreeable is that tool support for generic programming is just not as good as OOP. And in particular, the practice of C++ metaprogramming is performed in a way that it's actually used for both generic and generative programming. And well, it's been known for a long time that this practice has a lot in parallel with functional programming languages. And I think the first time that I read that was in Hosstein's book. He alludes very, very quickly about this. And then there is a literature on it. So people have been thinking about this, and in particular because C++ metaprogramming suffers from two very important things. First of all, its syntax is awkward and spontaneous because it was basically, C++ was basically never designed for metaprogramming. The other thing is that you often get very, very bad error messages that they just have lots of noise connected to them, and it would really take a lot of expertise to dig down what is there until you get to the mistake that you can actually. Whereas on the other hand, functional programming languages, they usually ship with very nice syntax, and they also, most of the time, have very expressive error messages. So people have thought about the parallels and thought, okay, why should we not just take that as an advantage and see what functional programming languages can do for us? In the paper we speak about three functional languages, Haskell, F# and Scala, and see whether they can facilitate C++ MP. In this talk I'm going to only focus on Scala. Okay, so our driving example of the paper and in this talk is a combined type ADT for rational numbers. Central to that is the greatest common divisor. In order to, you guys all know enough generic programs, I'm not going to go deep into what these codes are actually doing. One above is the combined time meta function for doing GCD in C++. The one here in Scala. Things to notice is that despite the fact that C++ is an imperative programming language, the practice of metaprogramming is immutable. So like functional programming languages, you have immutability. The other thing to notice is that in functional programming languages, like any of them, including Scala, the order of pattern matches is important. So the first successful pattern match will always be chosen. For example, if I switch these two, I'll run into an infinite loop. Whereas if there were more than one specialization here, the relative order was not important. So long as they are in scope, the best match is always chosen. The other thing, just a nitpick, is that in Scala the only unsigned type is car, which is a 16-bit thing. I seem to remember the last time I checked it. That doesn't quite scanty long unsigned of C++. So if you need that type, if you need something as large as that, you would need to program the ADT yourself in Scala. Now, then, the central part is the representation of these ADTs across the two languages. Well, I have broken the lines in a way that you would see the corresponding line on the left in C++ MP in Scala. It's quite straightforward to follow these things, I hope. Things to observe again is that in the same way that you have the practice using these things to catch errors in the compile time, you have to require a Scala. You have member functions, you have data members, you have member functions. So good parallel between the object encapsulation, and quick note that this ternary operator is the same as the if-else of Scala. So, some commonalities we saw. Let's go into the operations that you can do into on rational numbers. Again, broken in unusual ways for you to capture the respective lines of code. Things to notice. Well, first of all, dotted expressions here, whereas here you would just repeat what is over there. N is repeated. The other thing is that, well, here you just mention what you want to return. There is nothing for you to say that this is just what I want to return. I'm not going to name it, whereas because in C++ MP there is no built-in support for deliverables, you would actually need to name things. So, for example, here I'm naming my deliverable as type, as it is quite common in C++ MP word. Nice thing in Scala, you have this underline for when the actual material is not needed, the wildcard. And we also have extra name binding for where you don't want to repeat things. These two very last things are the ones that make this bit much more compact than this bit. And as you can see, it's quite a mess here. It's such a syntactic noise. This is something that we really want to escape from. What else? Right. The other thing to notice is that this is a complete specialization of a template, whereas this one is a function that continues to the next slide. So, next case, over there we have just a case statement. It's within the same function, the pattern matching, whereas this part we are providing another specialization of the general template. Things to notice. We are doing plus and we jump into minus. If I would have shown you the minus thing, you would notice that there is mutual incursion going on. So this is yet another commonality between these two words. The other thing is that, well, whereas on this part you're just going through the functions that you would need to call afterwards, on the C++ MP, you would need to acquire the deliverable, perhaps several times, and then say, okay, on top of all that, this is my deliverable, I'm going to forward, for example, type again. This is what we call in the paper nested entity forwarding, so you forward the job between the nested entities. Okay. To summarize things, I'm apparently going very fast, but okay, I'll slow down a bit. To summarize things, well, so let's take a look into what is common, what is not common, and whether that is going to help us to automate this process. So on the left, there are things which are common in the practice of C++ metaprogramming on the right to the Scala. You can read it much better than I guess. So first thing which is different across the two is that in C++ MK, you mentioned the general case in the top, and then you mentioned the specializations. The relative ordering of these things is not, it doesn't matter. C++ always chooses the best fit, whereas in functional programming languages, the first successful pattern match is always chosen. Now this is something that that is only syntactic. If you follow the paper, you notice that this very row is when we discuss the matter in the syntactic level. It's to see whether you can take this into consideration wisely for any semi-automatic translation. If you want to do that, what you need to do is to make sure that across the languages you just shuffle things in a different way that is more sensitive to your host programming language. Static assertion available both sides, that's a plus. Object encapsulation available both sides. Default values for parameters, this side it is available in the compile time, this side it is available in the runtime. Data members available both sides. This part, C++ lacks something, and that's the lack of deliverables to mention automatically, so that there is no built-in support for that. Whereas in functional programming languages, you always have the built-in support. Well, this bit turns out to be quite tricky. I'm going to go back into a bit of my slides. So here, for example, you notice that GCD is actually a value, whereas these two guys, numt and dent, these are types. For any automatic or semi-automatic translation across the two words, figuring it out when from here to here you would make it into, you would translate the thing into a value or a type is quite a difficult job. So this is when the human expert needs to jump in and perhaps do an involved job. The other very tricky one is that it is quite common in metaprogramming that you often mix templates and pre-process and metaprogramming. And this turns out to be quite difficult if you want to do some translation across the two words. This is very difficult actually to do. And I can give you some examples if the time permits, and I guess it will. So that's it. We think that this one, although it is semi-automatically possible, it's again going to need a lot of involvement from the human expert. And this is a semantic thing, so we think that if there is going to be any correspondence between these two, then it's at the semantic level. The other is that because of the difference between the way that these two words perform pattern match, it turns out that sometimes you would actually need to break your problem in different ways across the two languages. So, for example, There is an example in the paper where we perform equality. So if you want to test equality across two fractions in the C++ MP word, then if you implement the algorithm in the same way that you would do it in functional programming, you would get trapped, because for the case of 0, there is no best fit in the two specializations. Whereas in Scala, as like his all functional programming languages, the first successful pattern match is always chosen, and therefore you just don't need to split things in a different way. Whereas in the C++ MP, you would have to break them differently. So this is yet another semantic difference. Now, when we consider all that together, we realize that, well, even though it looks like semi-automatic translation is possible, it's for the very two cases where it's semantic, you actually need huge involvement from the expert. And the other thing is that, well, actually that is when these things get into the level where you have quite a big involvement from human being, and it just goes out of your control when it's in the automatic part, then there is a good likelihood that these things are not scaled, and more than that, it's error prone. And as we discuss in the paper, there are very simple cases that if you just miss, and when your code base gets big, it's very easy to miss those things. Then you might actually cater very subtle blocks. Now, what we take out of this is that, so okay, we have discussed the commonalities and the differences, and out of that we were hoping that we could get a semi-automatic translation across the languages, but perhaps because these three are very involved, it's a better idea that we can have a front-end DSL for doing neat C++ MP. Now, what that front-end would need to have is, first of all, we saw a lot of FP in C++ MP, but none of that was directly supported by the language, so maybe that's the time to actually think about the front-end having those things as a built-in. Well, the Scala syntax seems to be quite terse and beautiful, and it fits quite well with, it fits very close actually to the C++ MP, but there are bits of resemblance that you can even further work on and make it actually, despite being terse, you can even make it look like, well, make it more natural to the C++ audience. This bit is perhaps the most difficult part when it comes to the templates and pre-processed mixture. The front end has to have a very good support for that. It has to deliberately mimic the practice in C++ MP word. The pattern matching bit is also quite subtle. It has to mimic the exact mechanism in C++ MP. The thing that we didn't speak about here is that, well, C++ templates, they are very lazy in its lazy evaluation terminology in certain ways, but the practice is different from what they are. So templates by default are lazy evaluated with selective strictness, whereas in practice they are used the other way around. So it's like if they were strict with selective laziness. This is quite an unusual mixture of these two features, and if there is going to be any front-end DSL, then the front-end DSL has to well mimic the strange mixture. Okay. Any questions?
First, let's thank you, speaker.
view of the paper. So one of the things you mentioned there was that automated translation is not feasible, and maybe Jeremiah has something to say about it.
Well, my first question is actually going to be about the relationship with C++ 11. Now that there is context for and template type defs, a lot of the things that were the most verbose that really required workarounds are now covered in the language. And many of the cases where you need mixed preprocessor and templates was to emulate variadic templates, which are now a native part of the language. So it would seem like your domain-specific language now, C++ 11 is at least some of the way there.
That is indeed correct. The thing, though, to notice is that C++ 11 isn't fully shipped, as far as I know. And it turned out the last time that I checked it, maybe I'm not very updated, but context, for example, it turns out to be quite difficult.
Well, constexpr is not that popular, but still, you know, the static const thing is there. You don't have to do type wrapping nearly that often.
Yeah, sure. There is no doubt that C++ 11 is a much better tool for doing generic programming. What is yet to be studied is whether the added facilities will just grow even more script practices that then need to have a better front-end DSL that is at that level facilitating.
True.
What I really wanted to get out from you, Jeremiah, was that about scheme to template evaluator. How feasible was that?
Oh, well, I mean, I did one. It was practical without mutable state. When you added mutable state, then it became really, really slow and impractical.
So it could not handle
Well, it was like
evaluator itself.
Well,
translated to a template metaprogram.
Well, but what I was doing was compiling from scheme with mutable state, which is a lot harder to emulate in a functional language. But no, your basic scheme is easy to do, and I believe somebody's actually done an ML implementation or translator to template metaprograms as well. I believe that's actually publicly released.
Okay, then I need to come to you after.
I guess it doesn't still invalidate your claims that automatic translation is it's a different story whether it's practical and whether it's something that you would use in practice.
Well, I mean, for a pure functional language, it shouldn't be that difficult. It's not that difficult.
So one of the things you in the paper you mentioned that there's going. I started reading it and thought, well, why does we keep talking about translating from C++ template metaprograms to Haskell or why on earth would someone do something like that? But the point was really that, well, if you can't do an fully automatic translation, you will not maintain the metaprogram that maybe you would generate. You don't maintain them in the source language, but you might do modifications in generated metaprograms, and then at some point you might want to go back and you want to have this reverse full round trip engineering going on. But so that definitely makes perfect sense now.
Thank you.
And that seems to be usually most template metaprograms probably are born within a C++ program rather than you don't set out to be able to do this constraint solving library, simple C++ simple metaprogram or something, but you do some other library and you end up doing realizing that you need a little piece of meta code here and there to guide your library somehow, and then it grows and you need a little bit more, and then you have this big mess that's no longer maintainable. And at that point, you might want to come out of it and into some more sane setting. So it's definitely interesting to do. Yeah, I think that could be helpful. What asking like what my questions are really we'll have some ideas and now we can see that what kind of mappings there are between this weird language and some other less weird language. And there's kind of limits that you can't go past. You have to do manual translation here all the time. So what would be the ideal world? I mean, you mentioned that, or ideal and practical solution for doing metaprogramming within C++. You mentioned that maybe some kind of DSL. Jeremiah mentions that there's these new features of context expert, for instance. Practical already requires a C++ evaluator in the compiler, right? And because it has to, some of the expressions will have to be evaluated in the compiler. It has its limitations. I believe you can't use it in a type context, right?
You can't use it to compute types, no, but you can use template type depths to at least make it less messy.
Right. But are there, you see that if these kind of restrictions were lifted, then you could actually do C++ metaprogramming in C++. Would that be a better option than some other languages? Maybe I'll leave that as a longer answer.
Well, C++ is a big community, and part of that means that any change you want to make in the language, you have to have a very, very heavy weight in the community. And it turns out that the fraction of the C++ community which does metaprogramming is quite small, I believe. Most people, actually, I was watching a panel for C++ and beyond this year with Andrea Alexandrescu, Herb Campbell, and Scott Myers. And they seem to be very much convinced that the priesthood of this community, the sub-community, is not that much valuable to the rest of the community, so that they have enough driving force for entering a lot of metaprogramming facilities into the language. Now that is a very sad thing to hear from me, but if in an ideal imaginary world this would have been possible, I would have thought that the best idea is that we just rethink the matter in the sense that we say, okay, we have C++, people have been doing metaprogramming in it. Let's actually do things which have built-in support for metaprogramming. But I don't think that's going to ever ship.
So, actually, I'm going to disagree with what you just said. Even though a relatively small fraction of C++ programmers do serious metaprogramming, and they may not have much influence in the C++ community, they are very well represented on the committee that sets language features.
Correct. Whether they would like to take their own personal opinions in, or they would like to represent the rest of the community is a more important question.
Right, but I mean, when they represent their own personal opinions, and that is a lot of what they do push metaprogramming in.
Okay.
But also there's been a project that David Van de Voort did, this metacode thing,
yeah,
which was trying to put in a lot of the language features. They didn't go very far.
Correct.
But, he was at least trying to implement the sorts of things that you would want.
That's the direction that I would, in the ideal world, go into. But I'm very hopeless on it, I have to say.
And David is one of the people on the committee who's heavily involved in implementing C++. So if you had something compelling, especially if you had an implementation, they would probably be very eager to consider it.
Yeah, it's not impossible to.
It's not impossible. It's not impossible. Yes, you're right.
Others are not speaking kind of thing.
Are you, Jeremy? Are you following, or should I just?
I would,
Yeah.
well, I've taken up too much of the time already.
Yeah.
I have a couple more questions.
Let's have
Okay.
a few more questions
We can
elsewhere.
discuss it
I
later.
think coming before is a front and just programs. Coming before or coming over. Coming before.
No, no, no.
It's a front and just program. And in the release of Ocampo, we can link the compiler to the come before. We can link the whole Ocampo compiler to the come before. And then we come to the command time evaluation or using the same code impact on the normal Ocampo code.
Okay, that's something that I wasn't aware of. I need to take it. I'll take it offline with you. Just to add more on what you mentioned about this, why would you want to go from C++ MP to a functional programming language? As we have spoken about it in the paper, so when you have a problem that you want to tackle, it's in the software engineering world, it's quite common that you go back and forth between your design and your implementation. You can't really foresee everything in advance, and so there is this cyclic integration of new features, and because of that nature, when you come to consider your functional programming languages as your design phase and your implementation in C++ MP, you would, in the same fashion, need to go back and forth between the two.